We are Pratt & Whitney. I'm Brent Staubach. I work in the systems optimization area. And we've got John Schmitz, who works in power thermal management systems. And we have Nikendra, who also works in the systems optimization area. So we wanted to just come out, talk with you guys a little bit about the nature of systems optimization, some of the challenges of it, where we see things going in that direction, but also ways that we like to work with UConn. There is this IASE activity going on now, and that's something that we obviously want to exploit and work through. I think as you see as we talk, our systems are so coupled now between the engine and the airplane that it's very hard sometimes to think of them as two separate things. They really do work together as one thing, especially as engines and aircraft are getting more sophisticated with their control systems, with things that they can vary. You start to get a lot of dynamics and interplay between the aircraft and the engine. So what we really wanted to do, our talk here actually is going to be pretty brief. We'll probably talk a half hour, maybe 40 minutes. And then just kind of want to have a conversation. I want to see where some of your guys' heads are at, see where some of the students' heads are at. I got some charts in here talking about ways that we've worked with other universities that have been very effective. And I think the IASE activity is modeling after some of that type of stuff. But we've had pretty good engagements with other universities where we work with students to help them along and do internships and research to help further our capabilities at Pratt & Whitney. So you got a clicker or a button there?
In front of the desk.
All right. So what I'm going to do is I'm going to talk and babble, and John will help out. He is much more of an expert in the area of PTMS, and I will define PTMS shortly for you. So first thing, why we're here. I actually love working with the universities. We have a really strong relationship with Brigham Young University, where we bring students in. They have a department where they really excel in parametric CAD, parametric modeling, and they work the theory of it. So when they come in, I find we bring interns into Pratt & Whitney that can actually operate at a higher level than people that have been sometimes 3, 4, 5 years at Pratt & Whitney. And we've had a great relationship with Brigham Young University, and we'd really love to start getting into that type of relationship with UConn.
So any particular CAD tools you use? Or?
We use, at Pratt & Whitney, down in East Hartford, we use NX. Okay. Up in Canada, we use CATIA. Okay. The companies we have to interface with tend to be either CATIA or NX.
Who makes NX? I know we are dealing with the Joeseph systems.
So that's CATIA. Okay. Yes, we don't really work with them, but we do use Dassault Simulia's eyesight. Okay. We don't really use what is it, Modalogics? Modalica. Yeah. That much at this point. That's something we're peaking at.
So yeah, we're basically dealing with both DS and MathWorks. So.
Okay, yeah. But I'll tell you, the principle of working through commercial software is huge. Because first of all, when you get into industry, you're going to work through commercial software, right? No one's really going to care that you can write a little C++ routine and do something with it. You have to work with, the major software packages. That's how you will conduct most of your work. Universities, you teach and practice through the commercial software packages. We've found that universities can often be better interfaces with the software providers. Mm-hmm. Personal experiences I had with Georgia Tech and the ASDL lab, Aerospace Design Lab, is they actually drive the development on the SAS JMP product much more effectively than we ever could. Mm-hmm. With Brigham Young University, they work with all the major CAD packages, and they can drive improvements into those CAD systems more effectively than we can. Sometimes when you're very tailored into your whole, life cycle management system, there's very particular things that a company has to work with a software provider. But when it comes to new capabilities, universities should actually consider themselves as potentially being better equipped to do this than industry, especially if you form good working relationships.
Yeah, so you can answer that. NX makes that?
Oh, I lost track.
It's Siemens. No, Siemens.
Yeah, because they've been bouncing around. I lost track of who actually runs them right now. But to me, what it's about is in industry, we have a sense of future challenges. And what we're looking for is, new heads, new brains, new views, new vision. So that's kind of what we're really poking at here. The area that really intrigues us, though, in particular potentially with UConn, is in the area of energy management between engines and aircraft. It's a very rich system to work. There's not a lot of schools that are dominant in this area. There's pockets of schools that work on this, but it's something that is going to really dominate the next generation of commercial aircraft as well as military systems. I put some military pictures up here. They kind of look cool. The power loads on either commercial or military systems are going up huge, right? Everybody wants to have their electronic gadgets and toys on airplanes for commercial, and military has all their things they do. So there's more and more need to pull power off the engines, right? And when they use that power, it generates incredible amounts of heat that have to be rejected back to an engine. And that's what we refer to as power and thermal management systems, or PTMS. And in this context, really the engine is the power source and the heat sink. It's the only thing that can produce enough power on the aircraft. You can have batteries and stuff, but it's just not on par with what you can get out of carbon-based fuels. And in terms of rejecting heat, aircraft kind of have to be aerodynamic. You don't want to hang radiators and stuff off an airplane. So the engine has the airflow to reject heat into. And that's the area that we really find intriguing and interesting. And I think there'll be a lot of opportunity to work in these areas. And I actually there's an opportunity for UConn to assert a leadership role in this over the years. It takes time to develop a department of capability in this area, but it's something to think about. So when we talk about power and thermal management, I already mentioned that the engine is really the only viable heat sink. But I wanted to point out, see if there's a laser in here. Yeah, there is. What do I mean by power and thermal management on an aircraft? The engine itself generates heat. Okay? It's a heat engine, so of course it does that. But in terms of, I'll call it almost like extraneous heat, you have to cool the bearings, you have to cool gearboxes. Where engines are going in temperature nowadays, they're getting very warm and they need active cooling within them. So the engine generates heat that has to be managed. But then on top of this, the engine provides the power to all the aircraft systems. So like I said before, it's really the only viable power source. So you pull electrical power off the engine, you power generators, pneumatic, you bleed air off the engine to drive systems, and hydraulic. You use hydraulic systems to control things. Sometimes the control systems on an airplane are controlled hydraulically, sometimes they're electrically, depending on the vintage of the aircraft. But there's a huge amount of power that is pulled off the aircraft such that it can do useful things with it, right? And it can cool things. If it's a fast airplane, you got to cool yourself with respect to ram heating. Airplanes can sit a long time out on the tarmac. If you've flown recently, you've probably experienced delays and sat out on the tarmac for a while. The sun actually puts out a lot of heat into an airplane. And then there's all the environmental systems. The cabins have the air conditions, the avionics. Electronics tend not to want to be hot, so you have to cool those, usually on the order of 50, 60, 70 degrees. So you really have to cool these systems. And then in some areas you have special systems that are on the aircraft that need additional cooling. The point of this, though, is all this power is going into the aircraft. A lot of these systems on the aircraft, not a lot of them, all of them have inefficiencies. So they generate heat. Right? Unless we figure out how to violate the second law, we're going to generate heat on the aircraft. So heat now has to come back to the engine. And there's kind of two categories of heat that come back into the engine. The first one we'll call low-grade heat. This is heat that is at a lower temperature than the engine. you think, how do I reject it to the engine? Well, I have to put work into it. I have to pump it up. I have to do something to it to allow that heat to be rejected into the engine. So, power that you take off the engine to drive all the stuff that generates heat, I have to now pull more power off to force that heat back into the engine. And then there's some components on the aircraft that are warm enough that they have a natural delta T to work with the aircraft system. So there's low grade and high grade heat that come back into the system. And that's really what we mean with a PTMS layout or energy layout of the system. From an engine guy's perspective, though, we live with the sins of this stuff being sometimes less than optimally configured. Right? The classic scenario is, you've committed to an engine design, an aircraft company's committed to an aircraft, all the subsystem suppliers have committed to their subcomponents to design those components, and then all of a sudden things start to go wrong here. Actuators take more power, pumps were inefficient, generators weren't what they thought. We start to get more heat flowing back to the engine, right? Now we have to respond to that, right? But we've already kind of started to set the configuration to the engine. We're doing full-blown design. We have 1,000 engineers designing things, and now we're getting requirement creeps. The size of the heat exchangers that have to fit in these fan ducts starts to get bigger. We have to bleed more air off an engine, right? And that becomes a major issue for us, right? If you have on order of 1,000, 1,500 engineers working this system here, and you're into requirements creep, you have those people essentially wasting their time on a daily basis. And that's when you start to hear huge numbers, right? In the aerospace industry, you'll hear big numbers of how much things cost, right? You can literally be throwing away millions of dollars a day because the overall system wasn't architected in a robust manner that was tolerant to these changes, and now you have thousands of people off doing engineering work that all has to be redone. So that's why it's a very critical thing to us.
Why isn't Lockheed doing the work?
So, it is really interesting. The WSCs, the weapons system contractors, tend to think of themselves as the masters of this. One, they are losing their capability. It's very apparent. We work with the Lockheed people. You have horror stories with Lockheed. They're not really on top of these systems. Two, they have a different perspective of it. They don't understand the engine interactions always. They tend to parse the problem. When you look at a weapons system contractor, when they talk about systems engineering, they tend to think of that as a very bureaucratic function, managing requirements documents. They don't view it in a live sense of dynamic interactions of what can happen. Now, if I have a perturbation over here, how that ripples through the system. They don't really have that expertise. They certainly don't have it any more than UTC. When you look at the UTC umbrella now with Pratt & Whitney, Hamilton, Sunstrand, and Goodrich, you start to look at us as maybe we should be much more assertive in this. And it's going to cause social issues in some places, and other places will be accepted, and we're feeling this whole thing out. But I've worked with Boeing, Lockheed, Northrop on this stuff quite heavily over the past 2 years. And what I tell everybody, I see no evidence that they can do this better than us. Right? In fact, I would say, and also working with the various government agencies, I would argue that UTC, in particular some of the work at the research center, they had a whole integrated activity about 10 years ago. We might actually have some of the cleverest paradigms out there right now. We view things as an architecture and how do you manage the architecture. We're starting to. I don't think that's percolated through all UTAS yet. But that's the type of stuff that we really need to propagate. So this kind of just sets the lay of the land.
The point, Brett, too, is that the airline, the airframe generally doesn't think of the engine as being an integral part of the system. They think of it as a line replaceable unit, basically.
Exactly.
It's just got an infinite sink and they can do whatever they want. They don't think of it in the context of an integrated system.
Right. Yeah, the handful of guys.
Well, the economics drives them that way, too, the commercial business, right?
So when we're in an arrogant mode, right, at UTC, we'll toy around the notion of, well, the WSCs, they wrap the skin around all of our systems. And in some ways, we have quite a high content of systems on some airplanes, like a 787. You know, we don't have the engine, but if you roll up all the other systems, we got pretty high content. So I think we need to be much more aggressive internally in mastering true systems, big systems of optimizations, of architecture arrangements. And we need to make that known and a marketable thing for us. But we need more heads that can think at that level, right? Because I think we have kind of like little pockets of expertise. And that's the opportunity with universities like UConn. So what I just described was kind of sets the lay of the land. But when you look out in the future, things are getting worse, right? And they're getting worse because in some areas we're getting better. For example, on the aircraft, on the power and thermal side, you know, I already mentioned, people want to have their electronic toys on airplanes. They take power, right? We want to have more sophisticated radars, right? We want to have more sensors on aircraft. We want to do all this stuff. We want to have aircraft that are more adaptive. You'll see commercial pictures where, you know, NASA or other agencies look at wings that fold up so they can move around the airports more effectively, all right? Something's powering all that stuff. So the aircraft loads are going up. On the engine side, we've been driving, actually, before I talk to, on the engine side, we continuously drive the Brayton cycle harder and harder, right? You know, we drive it to higher overall pressure ratios. That improves the thermal efficiency. And we drive it to higher T4s. That, again, drives thermal efficiency. But also what it's doing is making the core real compact and small. It's making it very hot. Means things spin really fast on it. As cores of engines get smaller, they spin faster and faster. So bearings start to require a lot of cooling on them. Actuators on the engine start to be more demanding, especially as we look at engines that have more things that can be adapted. Pratt & Whitney has gone to the GTF, the geared turbofans. Hopefully you guys know something about that. But, you know, essentially what we've done on our commercial product line is we've introduced an all-new architecture into the market. Rolls-Royce has always had their 3-spool arrangement for engines. Pratt and GE's had a 2-spool arrangement. With the gear, we can kind of set up to almost, call it a 2.5 spool. It allows the big fan on the front of the engine to spin slow, where the rest of the engine can spin fast. But that gear generates heat, right? It's got to be cooled. Power and thermal management system. So the loads are going up. And then you look at the heat sinks, right? Well, that GTF example I just gave, you know, where we can slow the fan down, make it operate very efficiently. The other thing we're doing is we're making the fan really big in diameter. And you've probably seen that on commercial aircraft. If you look at commercial aircraft back in the 1960s, they had these little itty-bitty diameter engines, right? And you go to the 70s and 80s, bigger diameter. Well, the generation now are even bigger, right? What that means is we're moving a huge volume of air with a very low fan pressure ratio. That means any losses in that stream become very sensitive to the overall cycle performance. And you can imagine, like, if I have a fan pressure ratio of 2 and I have a 1% pressure ratio loss, or another 1.01 pressure ratio loss, I kind of effectively go from a FEEP or a fan pressure ratio of 2 to 1.99. It's not that big of a deal. But if I'm down at a 1.2 pressure ratio and I take a 1% loss and I go to 1.19, now all of a sudden I'm starting to give up all this benefit that I got by going to this geared system. So these low fan pressure ratio streams means it becomes hard to reject heat into these things. You might say, oh, it's cold because the pressure ratio is down, right? Isentropic relationships, it's going to be colder, but much more sensitive to loss. Fuel flows. We're doing this thing, making engines much more efficient. What does that mean? They don't consume as much fuel. So the fuel flow is a lot lower. We use fuel as a way to dump heat. Right? We dump a lot of heat into the fuel. I can't remember the numbers that we heat the fuel up to, but it's appreciable. You definitely wouldn't want to stick your finger into that fuel after we've dumped all the heat into it. And I already mentioned how the compartments around the engine to handle PTMS systems is getting smaller and smaller, because when you push these thermodynamic parameters on the Brayton cycle, the engine gets smaller and smaller. And then in terms of fuel and oil temperature limits, there's technologies to increase that a little bit. It's like, oh, can I get an extra 20 degrees into my oil temperature? And yeah, important, nice big technology, but it doesn't stack up against the overall magnitude of the problem. You add all this up, and now if you make this up to a poor overall PTMS architecture, that say somebody decided they need to have a generator or a motor on the aircraft operating at 85% efficiency, and they need that because they got to get weight out, because they're being feed on to get weight out. That person has no visibility into the fact that that 85% generator or motor is now producing all this extra heat. That means we got to upsize our heat exchangers. We got to bleed more air off the engine. So I'm kind of alluding to the whole system dynamic between the engine and the aircraft subsystems. So if you don't have the aircraft systems architected correctly, robustly, and have a mastery of it, the engine has got to eat all this. So that's where what we see is there's this huge opportunity for managing the thermal environment of the engine and the aircraft systems, the power environment, how all that, it's essentially an energy optimized aircraft. You can think of it that way. And that becomes the big thing that we get excited about at Pratt & Whitney. We've been pushing this concept very aggressively, working with UTAS, working with the Research Center. And I think as I alluded to before, we have pockets of expertise. And that notion of having a local university that could be engaged to flow new minds, new thinking into this problem is very intriguing to us. So, this picture almost alludes to the fact that collectively at UTC, we have hideous approaches for even diagramming the problem. It's classic how we do things. You have, all right, various ways of managing power or dumping heat into fuel, hydraulics or fuel hydraulics, electrical, and various things going on. So it's kind of alluding to an architecture. I don't want to get into the details of all these things because it's any one of these charts can become almost incomprehensible. But when you look at this in the totality, there's a huge number of disciplines that have to be engaged in exercising this. There's aerodynamic devices in this thing. Obviously, the engine is a Brayton cycle with compressors and turbines. When you look at the secondary systems, you have vapor cycles, you have refrigerant cycles, you have air cycles, you have heat exchangers, all that stuff. Intense aerodynamic work, heat transfer, thermodynamics, the mechanical design of systems, structural analysis. When I look at a heat exchanger, is it going to crack? Because a heat exchanger, you can think of it, it's a device designed for thermomechanical fatigue. It gets hot, cold, hot, cold, hot, cold. It's going to break. So, the whole mechanical design of things becomes very critical to this. A lot of the stuff that we do rotates, so rotor dynamics is critical. You look at secondary systems on the aircraft, they almost become little mini gas turbines. They have little compressors, little turbines spinning incredible speeds, and they can, depending on what type of aircraft they're on, get jerked around quite a bit in their operating requirements. So you get rotor dynamics challenges. Metallurgy, we always want more sophisticated materials on things. Manufacturing practices, additive manufacturing is a huge thing that's happening in our industry now. How do you exploit additive manufacturing to create heat exchangers that package more effectively? One example. Controls and sensors. That's a real interesting topic. I can probably pretty much guarantee most conversations you probably had with UTC or anyone at UTC or in the industry almost views controls and design as two separate worlds. And it's almost to degrees like, well, you design something and then you expect the controls people to figure out how to make it operate the way you intended. Modern systems now, because of some of the adaptive nature of future engines, being able to vary compressor geometries, being able to vary airflow in engines, control bleeds, actively control clearances, and controls in the secondary systems. Essentially be able to manage this power grid on the aircraft and to say, there's going to be a peak load here. maybe what I need to do is not ask the engine to do this. I need to grab something off a battery for partial storage. This notion that I have all this flexibility, controls all of a sudden starts to become not a secondary concern. And I hate to say that because probably some controls guys and head would explode. But they actually become the discipline that needs to be involved up front in the concepting. And that's something to bear in mind. And it's something that I think we really need to instill in our next generation of engineers, is that controls is just another design freedom in the conceptual design space. You need to stop thinking in terms of steady state stuff that I do. Time is extremely important. And the fact that we historically have ignored time in our conceptual design process is why we build margins, sometimes excessive margins, into our designs. Right? I have, say, a compressor on an engine. Right? Compressors, you put more speed into them, they pump the flow up more, you start to back pressure them, you'll start to push them into an unstable mode of operation, and all of a sudden the flow can actually almost throw up out of the engine. They call it a stall. You have to build what they call surge margin into a compressor. A lot of that surge margin is to handle off-design operations. So if you have an ability to control off-design, if you have new ways to manage things off-design, you don't have to build that type of design margin into it. And that's an example of how putting controls and sensor thinking up front in our processes can really allow us to reduce margins, which then becomes opportunity to improve performance. And performance is very central to us. The other thing I want to point out is computer science. Up until now, engineering pretty much operates the way engineering does. They bring mechanical engineers, aerospace, electrical engineers into that arena. They're using tools that are so sophisticated now in computing environments that are so sophisticated that we need to start challenging the paradigm that computer science is something that happens off in another country someplace and manages our systems. These things are so complicated, especially when you get into high-intensity parallel computing, that we need to really think in terms of computer science as just another engineering discipline. And that's kind of a funny thought, I think, in a lot of areas, because the past 20 years have been, in the engineering organizations, has really been about outsourcing computer science. It's almost been saying, no, we can throw that over the wall. So I want to throw that out as a notion that people want to think about as they think about system engineering problems.
So don't you also have software running your engine? Or?
Oh, well, that's another, controls. So once you talk about controls, you got software.
No, okay.
Right?
Yeah, processors and that kind
of. And this stuff, one of the things, and this is an open forum, so I got a little restricted on what I say, but the way engines operate and the degree that you need to bring controls up front, because I've been pretty much, for the past 10 years, on the conceptual side. Before that, I was on the more of a detailed design side. What I've learned is through applying optimization methods to explore the design space, as we look at engines that are more adaptive, what we've had to do, or I shouldn't say we had, but what we have walked into, is we have started to invent control strategies to manage adaptive style engines. Right? And that's when about 3 years ago, the light bulb kind of went off in our heads, like, we're doing controls work. Maybe we better start talking with the controls guys. And it's interesting, you talk to controls guys, a lot of the algorithmic approaches are very similar. However, they tend to focus in on having models that are extremely robust, extremely fast, produce surfaces that are very smooth, that efficient gradient schemes can work on. Whereas the concepting guys are, when they come up with the control strategy, it's like, I don't need it to work in real time. Right? I can let this thing run overnight to figure out how to schedule something. And I'm happy. We've actually walked into, I think, more flexible control paradigms that now the control guys are looking at us going, oh, you can help us parametrically explore the space so we can figure out more efficient algorithms. Right. So there's starting to be this banter going back and forth, and it's really this kind of awakening that's happened over the past couple of years.
So there's this huge fusion that we need to think in terms of, it becomes control sensors, computer science softwares, and then all the traditional mechanical aerospace or design disciplines. You got to drive a synergy between all of that.
So one other thing I don't see is the hardware end of things, like
So-
computer science.
Oh, yeah, so what computer science there for me is lumping it all together. Hardware, when you get into distributed computing, very important. Pretty much on a weekly basis, we will trash a day's worth of running because some server crashed. Right? That's hardware.
You need your fault tolerant everything.
Yeah. High-speed communications between things. The whole Linux, Unix, Microsoft operating systems, jumping between them, data storage, chronically consuming data storage. We're probably not real efficient with data right now, which then turns it back onto the software world, the more efficient things we can be doing. How do you network not hundreds, but thousands and tens of thousands of CPUs? I think we're probably going to hit another threshold where it feels like high-intensity computing is going to become much more ubiquitous, where through hardware we have the potential to be able to grab thousands, tens of thousands of CPUs on a routine basis.
Cloud.
Yeah, and then the other one to think about is security. We work in an environment where we deal with both commercial and military, protecting data from foreign national, and being able to touch it is a very important thing. So setting those systems up is important.
And part of what Brent's talked about is the internal challenge. There's also the external challenge where we don't make the aircraft, so we don't own their models. And a lot of this future state isn't going to be enabled by having simplistic models of the aircraft. You're going to need something that another company runs locally. Do you try to port that into your system where there's a lot of proprietary questions on how you do that in a way that they don't give up how their systems function? Or do you find some unique way to connect it via an intranet or internet setup? Is that fast enough? How do you access computers under those situations? How do you deal with different software programs? How do you deal with complexities in the system that aren't driven by the physics, but driven by the way you try to solve a particular state? So those are areas that have not been resolved.
Which is usually how you resolve the physics, right? We have a very prescribed way of doing analysis, modeling, and putting things together. And that really just, it puts the blinders up all of a sudden, and now you can't see things. But John raises a good point also. UTC is very broad, but in the end, the aircraft company makes the aircraft. So you have to communicate with them. I don't think industry right now has a good paradigm on how to do that. I think we're still exploring that. There's one paradigm where we're just going to tie our models together. If you've ever seen industrial quality models, that's an insane proposition. The notion that someone from Lockheed could run some of our physics models is insane, because our physics models, they crash. They have all kinds of little idiosyncrasies in them. Right? Think about, for the students, think about, when you write code, right? And now you're just going to hand that over to someone else and have them run it, right? They're going to muck it up. So, do you really tie things directly together? Do you use surrogates or emulators? That's an area that we're exploring. We're actually engaged very heavily in that. That has limitations, though, right? Probably right now, I'll say 80% of our computational resources right now are consumed creating emulators to provide to the airframers. So that's a big area that I think is ripe for a new paradigm. Also, out in industry, you'll hear people talk about integration frameworks. You go into a Lockheed or a Boeing, they'll talk about, they use a tool called Model Center to tie their stuff together. You walk into Pratt & Whitney, Rolls, or GE, we all tend to use a tool called EyeSight. We tie our stuff together. If you go out to the Air Force, or NASA, they've done integration strategies. They've brought in third-party consultants. I think it was PK Krause, to create standards and a format to integrate stuff together. So there's all this stuff. And at some point, it's like people are thinking in terms like, I need this one Uber framework. And it's like, well, if everybody has their own individual frameworks, why can't they talk to each other? It's like there's got to be some simplified paradigm that we're missing. Students can be really good at that stuff. And I'll tell you, if you get students working in some type of collaborative exercise with another university, I've seen stuff. I mentioned work with BYU. They did an exercise where they designed a car, and I think they had like 14 universities tied in. Think about doing a PTMS project with other universities. Maybe you have a Georgia Tech doing some set of systems, and MIT doing some other systems, and you guys are the architects. They'd love that. But what you're doing is you're putting students in a situation of now they've got to do collaboration, right? They're going to now start to have the things fire off in their minds, like, oh, tie these two models together. Oh, my counterpart down in Atlanta, he can't make my model run, so I got to find a solution to that. Forcing students into scenarios analogous to where we are, I think it becomes a rich way to come up with new thought processes.
Yeah, it can also give insight into how you would validate hardware once you build it.
Right.
There's certainly motivation for everybody who has a commercial product to not spend as much money validating all their hardware before it goes out into service. You want to do as much upfront robust modeling to convince everyone that it's a safe system. But in some cases, there are these unknowns where you have to weigh the balance between testing a lot or testing less. The integrated modeling approaches that you may take on with other universities may indicate areas that still require validation of the hardware as connected, and that can take on a larger project within an industry.
Yeah, I think that's directly in line with the way that we are thinking. So in terms of requirements, architectures, you talked about model-based design and verification validation.
So being able to manage the systems of systems is really how we see being able to differentiate ourselves. Obviously, certainly at the UTC level, but also just Pratt Whitney from a selfish perspective, right? All of our past engine programs have been burned in some way or another, just literally burned by PTMS concerns. So we have a very selfish interest to operate at the UTC or UTPAS level. And that's why we've engaged people across the corporation. So areas of research student development that really excite us are listed here. And this does presuppose a foundation of understanding of basic turbo machinery, of basic thermodynamic devices, of control systems. So there is an assumption that you have that foundation built. But when you get into the discussion of what does it mean to have a meaningful PTMS architecture, should I have batteries? Should I have capacitors? Should I do it directly off the engine? Should I use a vapor cycle to help reject the heat? Or should I just use an air cycle? How should I do that? Should I use an intercooler in the system? There's so many things that these can be architected. What we're talking about is how do you figure out architecting it? Observation right now is architecting happens because there's one or two guys at your whole corporation that have prior experience and still work in the company and have an opinion on how it should be architected. And that's not that much of an exaggeration. I mean, I think literally when we go to like Northrop Grumman, I think there's one guy, right? I think he's probably pushing 70, right? And when he goes, is Northrop Grumman really going to be able to do this architecting? Now, yes, once an architecture is known, there's a lot of people there that can work on their pieces. But how do you put it all together? I think this industry is in danger. So, I'm focusing here on what does it mean to come up with an architecture. First thing is you got to have a level of abstraction, right? You can't just work at full-blown physics models representing everything in the weeds. You can't work at bench test levels. You have to abstract this thing. First, that really intrigues us is, can we create a syntax to actually represent PTMS architectures? Something that expresses all the connections, whether it be electrical, fluidic, mechanical, right, between the engine and the aircraft systems. if you have a syntax, and when I talk about syntax, it's like, just like, trying to remember back, actually when I was here, by the way, I graduated from UConn in '84, by the way, so I'm trying to remember back, like tensor notation, right, vector notation, right, very compact notations allow you to describe the equations of motion in a very compact, descriptive form. Can we have a syntax that can help describe how these architectures are all interconnected, right? And it may be that you create syntaxes that allow things to be connected together in a non-physical manner, and that might be okay because you lose something else to filter those out of it. But if I can at least have a way of representing the problem, and that is important. One, I think that helps people understand things. But if I ever want to represent this problem to a computer, I really need a syntax. And that's very tightly related to architecture, visualization, and diagramming. You guys may be very versed in things, simple things like design system and n-squared diagrams. That's really not that propagated through the halls of industry. Again, there's pockets of guys that see the world in that manner. But how do you visualize their diagram and have a syntax to represent these problems? If you have that, then you can actually start to think about it. You can actually start to bring computer resources to explore this design space, which brings in the notion of reduced order modeling, right? And when you're working at the architectural level, it may be very reduced order model, right? A heat exchanger might be just representative as some cooling effectiveness loss curves, right? It might be very high level like that, but it's enough to filter an architecture represented by that syntax to the physically meaningful architectures. At that point, you can actually now engage in topological optimization. You can start to explore all these different combinations of things. We don't do that, though. That's an area of research that we need help on. I think that's an opportunity. When you pull those things together, now you're actually getting yourself into a spot where you can do optimization. And I always like to use the word optimal and robust together, because I don't see them as conflicting concepts. I view robustness as a way of characterizing the nature of where you are in the design space. I am at this point in the design space where if I perturbate anything, not much happens. I'm robust. I'm in this region over here where if I perturbate, everything goes bad. When I talk optimization, that's about navigating through the design space. Right? So I use optimization to find robust regions. I'll use optimization to find pinnacle performance region. So they're complementary concepts. And if you bring those first four items together, now you start to have a chance of actually optimizing out architectures that are robust. And that last word on there, verifiable, is really important. We already are seeing evidence that we can create analytically systems so complicated that you probably don't have a prayer of ever verifying them. So you need to have that in your thought process right up front. That's working at a very abstract level. The next level starts to come into bringing in more physics, higher fidelity. This is more classic integrating physics models, a CFD model, a 1D aero model, a beam model. But you want to have that integration driven by the abstraction you created up here. People have been doing model integration, commercial packages have been out on the market for the past 20 years. You see it taking hold in industry over the past 10. And if you don't drive how you put your models together based on something like this, you end up with this free-for-all of plumbing tools together. And it becomes very unwieldy at some point. So you want to have your workflows derived from up here. And then that makes these workflows more manageable, and you can really go to very large-scale systems. And then what this starts to enable is architecture optimization in space and time. And I'm emphasizing time up here. Time is still up here. You're going to capture that in reduced order models. But here it's going to start to bring in more transient simulations. And you have an ability to exercise these architectures that you've selected up here to really start to evaluate them in greater detail. It allows you to bring more of the component designers into the fold. This actually becomes the system that ultimately will replace traditional requirements documents of issuing boundary conditions between components. What will happen in the future is you will have a model and you will query that model to understand your boundary conditions. And if the system is updated, then you will always be in sync. Because that's another product thing. In big systems, everybody's out of sync. It's amazing how much, somebody, a local person designing this component could be on, 3 iterations behind on their boundary conditions. So again, systems thinking is what we need to do.
What do you mean by space? Yeah.
Space? What I mean by space is you have all these design degrees of freedom. I can configure my engine. I could change the overall pressure ratio. I could change the fan pressure ratio. I could change my heat exchanger from a cross flow to a counterflow. I could change the fin types on it. I could change the fluid in a vapor cycle. These are design decisions. These are design choices, and you represent them parametrically. And that parametric dimension becomes your design space. It becomes this virtual design environment that your optimization algorithms, your DOEs help you navigate through.
I also think thermal environments for components. Some components traditionally have very low temperature limits. But if you can abstract it and begin to see the benefit of a low temperature component placed locally in a high temperature environment, what the overall system benefit is, it may motivate you or industry to go down a path of developing that capability. So there's some sense you could look at this to guide and identify holes in future architectures that are enabling for a particular capability. It allows you to differentiate yourself.
That is a very important concept, the concept of a design space. Actually, that might be actually something in industry we take for granted, that concept. Yeah. We really do view ourselves as having created a numerical universe that you move through by changing design parameters. That is the world that most analytical engineers work in. It's the world that most engineers that come into industry work in, because test engineers are getting to be a rarer and rarer breed. That's how you're going to experience design, is by manipulating the shape, the parameters of it. And that's your space. And that space exists both dimensionally and in time.
So is it fair to say that the reason why you're not doing the global exploration of the design space is because you start with the existing system and then, let's try and make it work for the new requirement?
That is our history, right? Which is why this is so important, right? And you can substitute in the words like platform-based engineering on here, right? That's bringing a layer of, levels of abstraction. And that's kind of what I'm working through. I don't know if that terminology has taken universal hold. I know the Darker guys loved it. They turned us on to that.
I think it was there even before the computer science case, that Kevin Otto's book has platform things.
The problem I have
and the computer guys have taken over things.
Whenever we use it within our world, we say platform, people start to think, the aircraft is the platform.
Yeah, right.
But that's essentially what I'm describing here is a platform-based.
Platform is basically a basic structure.
Yeah, and then with this, now you can, and here, you can start to bring in your algorithms. I lump everything under MDO. Some people get all antsy about that, like they think MDO is something to take out. I'm a designer at heart, so I view anything that drives me through the design space as being optimization. My design space is multidimensional, so I'm MDO. But it brings in, and this was certainly not an all-encompassing list, but just notion, your DOEs, your sampling of the design space, and then approximation models and emulators, very important in how we interrogate our design space. We do rely on emulators quite a bit to visualize our DOEs, and we are using emulators to communicate our design space to our customers. We will take emulators, essentially that represent this design space, right? Because we've parametrically represented our design, all these knobs that I just described. Well, that's what I'm running the DOE around. If I'm creating a response surface model or a neural net, that's what I'm doing regressions to. So now I have this emulator of all of my physics models that I use to evaluate that design space that can now either be used to visualize the space, it can be used to internally do robust optimization and do more intensive computing, Monte Carlos and stuff
So
like
basically,
that.
emulator is basically a function evaluator.
Yep.
Exactly.
Yeah, or we can use these to hand them off to somebody else. The whole notion of robustness characterization, the notion of the classic gradient schemes, stochastic schemes, visualization. This other one is something we don't know a lot about, but we know it's very important.
We have courses in that area.
Because one of the things that all of this stuff here, you walk into pretty much any company right now, they will generate gigabytes and gigabytes of data that get thrown away the next day. How do we start to say, I don't have to run an optimization algorithm again? I have so much data available that I can learn the space. I have learned how to navigate the space. I can train something. We've done rudimentary work on that. That's probably going to be 15 years ago. Training neural nets to kind of work in a delta space so they learn design trends. And that was very effective. We've done some simple things of using genetic algorithms to figure out what type of rules work and don't work to move through the design space. We did that stuff 10, 15 years ago, probably because we had more budget and time to investigate. We are just, pedal to the metal now. We need help in these areas. We have a sense that there's a lot of promise, potentially to really allow us to move through design spaces much quicker.
So you do have already data that's stored, and you've
Uh,
got this kind of points in this design space where the corresponding
Back
responses.
to why computer science guys are important to be involved in this.
Right.
Ad hoc. We store information very ad hoc. I got file server XYZ, chock-a-block full of data. How do I get it? Because on a file someplace we wrote down what the directory structure is for it. So that's another rich area. And in the future of engineering, it is going to be, this is almost an inevitability of where we're going. So we need to learn these things and figure out how to accelerate, how we're going to get there. The last one I want to mention, high intensity computing. I already talked about that. That's very important. The last one is this whole cyber-physical validation. These systems are going to be very complicated. They do need to be validated. The notion of creating an entirely physical set of hardware that will be tested and we will learn everything and all will be good there's probably a little flaw in that kind of thinking. What is more likely is going to happen, because it already is happening, is you're going to have a mix of bench tests, limited rig tests, and emulators of other components. And you're going to switch things out. And you're going to do it that way because you're going to have some components that are high risk, and you want to get them to test as quick as possible. And you're going to work in that manner. And this will then build up. In the end, there will still be an overall system test, because at some point this thing will fly. But that notion of cyber-physical testing and validation, the reason it's important to have that here is because that thought process needs to start up here. You need to be working all the way through this. You need to be working towards that environment.
Yeah, we basically distinguish among 4 different ways of validating, like a model in the loop, software in the loop, processor in the loop.
Yeah, I know the controls guys, I see them do this type of stuff, right? But again, that's part of the learning. So we've got to figure out how to get controls, learning and thinking into the broader community and vice versa. This whole system is going to be so dynamic. So
I think this is exactly the way that we are thinking about our both our research and the curriculum.
Yeah, so the way we were thinking of engaging UConn with this stuff is kind of this crawl, walk, run philosophy. And we work with the research center guys quite a bit, so we have some familiarity with thermal fluid system courses that are being laid out. At least we've seen the SE 5101 course, which looks like a good foundation. Turbo machinery, components in it. And I saw some of the control stuff.
Quite long too, yeah.
Yeah, I haven't seen the other courses. But what we would be interested in is saying that this is good, but I want to bring the jet engine cycle into it. And you probably need to have a little more representation of a jet engine than what's being considered in that course. You really would like to have a jet engine cycle course in here. And that's something Pratt Whitney, we have created courses like that. We could work with the research center. It's something that I think we ought to throw on the table. And then systems optimization. I'm sure you have optimization courses, systems optimization courses here, but then to tailor them in terms of everything I've talked about up until now. Right?
Yeah, it's basically, we have things in nonlinear programming, linear programming,
Yep.
combinatorial type of thing, and optimal, like a dynamic programming and model predictive control type of courses.
And then with that,
Yeah.
and some of the foundational stuff up here, and there are a few more things here, now you can actually take on the high impact problem of the engine. And I was envisioning bringing, it doesn't have to be a vapor cycle, it could be an air cycle, but the system that's going to essentially allow heat to be pumped up to get into the engine. And that brings in itself more turbo machinery, whether it be a turbine expander. This is just showing bleeding air off an engine going through a heat exchanger into a turbine expander. Now you've dropped the temperature way down such that that can be used to run through this heat exchanger that is taking heat out of a vapor cycle here with this compressor and then the aircraft here. Now this is like the dirt simple. I'm not saying this is an efficient cycle, it's just a representation of one. And these things can become very complicated with compounded loops with intercoolers in them. You can have multiple vapor cycles to kind of jack the temperatures up. It becomes a rich area of topology. And when you come back up to here, where should this heat exchanger be bleeding air off of? This heat exchanger in here has an interaction with this fan. Right? If I start to load the fan up, should I now adjust the fan pressure ratio on it? Or potentially, I should say, I'm not going to use this fan at all. I'm going to use a separate blower in an airstream from ambient air.
So in that state, you begin to see your thermal fluid designs influence the engine architecture, as opposed to the thermal designs always working around within the jet engine environment and subjected to their particular design constraints. Now the system can be given to influence design constraints on the engine design itself.
Yeah, you could basically influence our robust design course. So in the thermal systems design thing, we have our second course is on robust design and system optimization. So so it looks like what you want to do is maybe add another track on the jet engine cycles. Is that what?
Notionally, yeah. Right. And it could be a full-blown course. It might be something that you want to leverage from Pratt Whitney. I don't know what you have right now. I have not engaged UConn for a long time. I don't know the status.
Okay.
What was that, Ruby?
We can have a track. There's a set of 3 courses in a project that gives a certificate program. So right now we've got 3 tracks. We can have a full track on the jet engine side.
Well, and it may or may not be a track on the engine. It may be to do these tracks that you've already defined. You need to beef this up because you want to drive total system thinking, right? And we will very quickly bring ourselves back into UTAS box, Pratt Whitney box. And it's like, that's the thing that I really want to break. Right? And one mechanism to do that is...
So basically the lower thing is UTAS and you guys have the other one. I can see that.
Yeah. And from the tracks you have, like I said, it may not be that you want a whole engine track. That may not be the thing to go down. It may be just that in the tracks that you've already had, you have a course on the engine.
Rather than the fuel system?
No, you need more in the fuel system. Yeah, you need a lot more in the fuel system.
Right now we have ECS, there's a climate control in the aircraft, chillers, and the fuel system.
Yeah, and what I'm worried about is this engine's static with respect to that. I want to make sure that the engine, well, first of all, the engine can be redesigned and changed up front, if we know about it up front, to make this system better. Because when you look at it as the aggregate of all of this, that might be the best trade. That's the mindset, right? So to me, that's why you need to have a full-blown engine representation in there, where somebody can do parametrics on the aircraft. Now, you might not have to get all the way down into doing rotor dynamics and all the glorious details of an engine, but you definitely need something that can be exercised at a conceptual design level for the engine. I think it's well, I'll say, it's just extremely important thinking.
Brett, two things. I think that, there is a turbo machinery course within mechanical engineering. It focuses on compressor and turbine aerodynamics. Maybe not so much the cycle, but there could be a foundational starting point. Number one. Number two.
Is Lee Langston still teaching?
He's here. I don't know that he teaches. Tom Barber teaches the turbo machinery.
Tom Barber,
Tom
okay.
Barber teaches turbo
Yeah,
machinery.
Tom Barber.
Right. And the other thing is that you're right in the sense that today we, and I'll put myself we, because I still think I work there, right, would make optimization decisions based on the engine for what we think is the engine performance in the right cycle. We don't make decisions based on the integration.
Yeah, it's not in our DNA.
We never make a decision that says we're going to change the Oprah because it's a better system design.
Yeah.
Right? And that's what you're trying to drive. You're trying to get decisions made with a recognition of the implication of various system architectures.
Right. So that's what the engine's important.
But it's a really strong thing if you can walk up to an airframer and say, my engine design simplifies the design of your aircraft.
Yes. Yeah.
Yeah, that's a powerful statement. But it's laying the foundation.
This could be our capstone design project. Would you have a fourth thing? They will basically learn the lower part as part of a thermal fluid systems course.
Yeah.
So maybe they can do that capstone type of thing.
Which gets into the projects, because if you have that foundation, it's like, don't be timid. There's nothing wrong with slamming students to optimize something. The worst thing they're going to do is come up with the wrong answer, and it's just electrons, right? I mean, that's a great learning experience. And having them do that with engagement with some guys at Pratt, some guys at UTAS, UTRC, I mean, it gets to be fun to do that stuff. So that's what I'm just throwing out here, obviously optimize components, explore architectures, look at the super system. This notion here, I threw this in here because we talked about this a little before, adaptive systems and controls. If you threw in an engine that has more adaptive features on it, and the systems on the aircraft that are more adaptive, suppose this system operates as a vapor cycle in one mode or one part of the flight regime and switches over to something else in another part of the flight regime. Right? Being able to control that, make that decision, be able to coordinate that with the engine, have the engine optimized with respect to that, and vice versa. Just go at it. And at that point, turn on whether it be a senior design project or some graduate projects, and start exploring that space. And then you start to build that culture of now to start to really work the innovations. And I don't know to what level you're trying to drive the stuff for UConn and the IASE activity. But I think there are a lot of areas for research and innovation here.
So we basically have three major thrusts within the institute. One is the educational component we mentioned, you're probably aware of. The second is research. In fact, there is an RFP that's coming next week.
That's on the research area?
Right, and the embedded systems and supervisory control areas.
Yep.
And the third area is the industry.
Now, do you think you can do research without these other elements, or are you just trying to get a couple things going in parallel?
Those are basically specific business needs. Right now we're working with BIS, Building and Industrial Systems, and also UTAS.
Mm-hmm.
So we would love to have you guys be participating.
I think on the innovation technology, we would love to participate in that.
Okay.
I would love to drive it so you start to have a clique of professors, students that can bring all this stuff to bear on it. And when we say that, we are thinking that this would be a long-term relationship. I'm thinking, this is like a 3-5 year journey.
Yeah, absolutely. We already have a 5-year thing right now with UTC.
Yeah.
There's a culture for systems engineering that acknowledges the system as being the primary goal, not your individual subset of the system.
Mm-hmm.
So you're not necessarily looking for the master of everything. You're looking for people that have the ability to work with lots of other different groups.
Right.
People that may not understand the intricacies, but understand that they have a sensitivity to something else. And then you learn that, you can either provide teams like in your project area, right? You can have comprehensive teams, electrical, mechanical, aero, thermal fluids, that work together. We've experimented with that within industry, and different corporate groups getting together in those sorts of environments, doing concurrent design and engineering. That could be a project. Those students that then graduate and go out now have a new selling feature associated with them to industry that they've worked in a systems environment. They've got some idea as to how to integrate. They're not going to show up and want to silo themselves away from everybody else. They're going to be out there trying to engage and develop a full system, so they're not going to be quiet when they see their particular area being compromised by something else. They're going to want to speak up. They're going to want to drive a good final state, not just the best final state for themselves or their particular discipline.
In fact, if you remember, maybe during I'm also a UConn graduate, so during our time, each department was different. This institute is basically bringing together electrical, computer science, mechanical, chemical. In fact, all the departments are involved in the research projects, right?
Yeah, oh, that's excellent.
Yeah.
Yeah, because I remember my day, it was very serious.
So if we consider that 3 to 5 years long period of relationship, I think this was a really good supply chains. So students learn from the course in the crawl, and then involving the project that is a small scale, and also based on those kids already educated of the basic understanding, and involving that project approach, and then usually we can capture them up to the innovation way, and
Absolutely.
eventually they will provide. I mean, we will provide them to the company UTC as well.
Absolutely. So, actually, following up on that, that is kind of our thought process. Start engaging UConn in this area. We definitely, I think there's a lot of value. So that's kind of what this conversation is, just the beginning of it, hopefully. Establish like a 3 to 5 year roadmap through the IASE process, through relationships with Pratt Whitney, and develop that roadmap. And there's some elements to it. We've already touched on this notion of having a gas turbine course, and maybe you guys already have the good basis of that. Maybe it's more than enough. Maybe it just needs to be tuned up or tailored, whatever. Tailor some of the SE, like those courses. So I look through the topics that are going to be covered in your first course. It seems like it's pretty comprehensive. It looks like
And it's a different way of teaching also. I'm not a thermal fluid guy, but the way that we have structured it is starting with the requirements, what the current processes are, what the new process is going to be, and the fundamentals, and then building component models, and then bringing them together to the system level.
Yep.
It also has a DOE.
Yeah, so I have it with me here. I did like the way that
And we'll make sure that we get all the 8 courses.
I would like to get that. Does you guys, the research have it, or do you have it? Or?
We have, I can.
Okay, yeah, definitely like that.
I'll take your card on that.
And then to
You've
work
already given me
through.
that actually.
Okay, yeah.
So, Brent, just so you know, even the course SC 501, 511 was like 20% to be taught by UConn.
Oh, yeah.
Yes.
And another thing that will be nice is to have the Pratt or UTC lecturers. And typically we would like to have people like at your level.
Engage the fellows.
You get the fellows and chief engineer level,
Have you approached?
Now, this is only with UTAS.
Okay.
UTAS and BIS right now.
Yeah.
I did approach senior fellow discipline lead of systems engineering.
The notion of sponsoring, working with undergraduates, senior projects, see a lot of value in that. I know some people tend to think, oh, they're just seniors and not graduates yet, they don't quite know what's going on. I've been very impressed with senior projects at other universities, and you have the coursework and enthused professors. You can get a lot out of this, and that is where we will bring